Let's run through 5 quickfire practice questions, then finish with a formal proof. Question 1. Gradient. Take f equals x squared z plus 3xy minus y squared z. Partial of f with respect to x, freeze y and z, differentiate to get 2xz plus 3y. Partial of f with respect to y, freeze x and z, differentiate to get 3x minus 2yz. Partial of f with respect to z, freeze x and y, differentiate to get x squared minus y squared. Stacking these together, the gradient of f equals the quantity 2xz plus 3y I hat plus the quantity 3x minus 2yz j hat plus the quantity x squared minus y squared k hat. Question 2. Curl. Take f equals yz I hat plus xz j hat plus xy k hat. So p equals yz, q equals xz, and r equals xy. The I hat component is partial of r with respect to y minus partial of q with respect to z, which gives x minus x equals 0. The j hat component is negative of partial of r with respect to x minus partial of p with respect to z, which gives negative of y minus y equals 0. The k hat component is partial of q with respect to x minus partial of p with respect to y, which gives z minus z equals 0. So the curl of f comes out to exactly 0. Question 3. Divergence. Take f equals x squared y I hat minus 2yz j hat plus xz squared k hat, so p equals x squared y, q equals negative 2yz, and r equals xz squared. Partial of p with respect to x gives 2xy, partial of q with respect to y gives negative 2z, and partial of r with respect to z gives 2xz. Adding these together, the divergence of f equals 2xy minus 2z plus 2xz. Question 4. Test for conservative, then find the potential function. Take f equals the quantity 2xy plus z cubed, I hat, plus the quantity x squared plus 2yz, j hat, plus the quantity 3xz squared plus y squared, k hat. So p equals 2xy plus z cubed, q equals x squared plus 2yz, and r equals 3xz squared plus y squared. Testing with curl. The I hat component is partial of r with respect to y minus partial of q with respect to z, giving 2y minus 2y equals 0. The j hat component is negative of partial of r with respect to x minus partial of p with respect to z, giving negative of 3z squared minus 3z squared equals 0. The k hat component is partial of q with respect to x minus partial of p with respect to y, giving 2x minus 2x equals 0. Every component is 0, so f is conservative. Now we build f1 equation at a time. Partial of f with respect to x must equal 2xy plus z cubed. Integrating with respect to x gives f equals x squared y plus xz cubed plus some unknown function of y and z. Partial of f with respect to y must equal x squared plus 2yz. Integrating with respect to y gives f equals x squared y plus y squared z plus some unknown function of x and z. Partial of f with respect to z must equal 3xz squared plus y squared. Integrating with respect to z gives f equals xz cubed plus y squared z plus some unknown function of x and y. Matching all three versions together, they combine to give exactly f equals x squared y plus xz cubed plus y squared z. Question 5. Prove that no such field exists. Take f equals xy I hat plus y squared z j hat plus 3xz k hat, so p equals xy, q equals y squared z, and r equals 3xz. Partial of p with respect to x gives y, partial of q with respect to y gives 2yz, and partial of r with respect to z gives 3x. Adding these together, the divergence of f equals y plus 2yz plus 3x, and this is not 0. Since the divergence of any curl must always equal 0, and here the divergence of f is not 0, no vector field G can exist with curl of G equal to f. Now let's finish with the formal proof behind one of the theorems we've been using, that the curl of a gradient is always 0 for any smooth scalar field f. Step 1. Set up the curl determinant using the three components of the gradient of f. namely partial f by partial x, partial f by partial y, and partial f by partial z as our p, q, and r. Step 2. Find the I hat component. Partial with respect to y of partial f by partial z minus partial with respect to z of partial f by partial y. This gives the second partial of f, taken first with respect to z then y, minus the second partial of f, taken first with respect to y then z. Step 3. Find the j hat component, negative of partial with respect to x of partial f by partial z minus partial with respect to z of partial f by partial x. This gives negative of the second partial of f, taken first with respect to z, then x, minus the second partial of f, taken first with respect to x, then z. Step 4. Find the k hat component, partial with respect to x of partial f by partial y minus partial with respect to y of partial f by partial x. This gives the second partial of f, taken first with respect to y then x, minus the second partial of f, taken first with respect to x then y. Step 5. Here's the key move. Apply Clairaut's theorem, which says that for a smooth function, mixed partial derivatives do not care about order. So each of those pairs of second partials is exactly equal to each other. Step 6. Since each pair is equal, every single component becomes 0. So the final result is curl of gradient of f equals 0, always, for any smooth scalar field. Before we finish, here are the concepts to take away. Gradient means stacking the three partial derivatives of a scalar field into a vector, one calculation per variable. Curl means building the three-row determinant grid with I hat, j hat, k hat on top, partial derivatives in the middle, and p, q, r on the bottom, remembering the built-in minus sign on the j hat component. Divergence just means adding three matched partial derivatives together, no determinant needed. For testing conservative fields, if the curl of a field comes out to 0, the field is conservative, and you can recover its potential function by integrating each partial derivative equation in turn and matching the results. For proving impossibility, if the divergence of a field is not 0, that field can never be the curl of anything, because the divergence of a curl is always 0. And underneath all of it, the reason curl of a gradient is always 0 comes down to one fact, that mixed partial derivatives do not care what order you take them in for any smooth function.